Okay, so here we'll continue our conversation with chapter 17, and we'll start looking at 17.3. So representation and visualizing these polyhedrias. So we'll start off with, what do we see when we look at this drawing here? And so some people might say we see a regular hexagon with some segments drawn, and others might see a cube. So we want to start being a bit more cautious on our vocabulary, but also, we could be a bit lenient in terms of when we want to start introducing and relating some of these images here. But no wrong answer here. Both of these would be acceptable, but we're going to start now trying to illustrate two or three-dimensional figures in a two-dimensional space. So it is helpful when we start to keep our vocabulary and in our drawings pretty consistent here. So we'll talk a little bit about those representations. And so what we would like to do is in the physical world, right, these physical world representations. So when we start talking about these polyhedrias, for example, a cereal box, a shoe box, trying to see some of these objects in real life. There's a lot of manipulatives as well that you could have. And just trying to represent these in different ways. It's worth just having kind of a day to play around with these and looking at objects that they're familiar with. And so they could start making these connections here. Because a lot of times they will have to do these visual representations kind of in their head, right, to start visualizing this here. So one, and depending on the age group here, but one activity I like to do is to have them start playing around with things that are a bit physical here is I typically give them, 3 markers, and I have them draw an equilateral triangle. And so after playing around with it quite a bit, most students are able to kind of come up with putting these 3 markers on a table and making an equilateral. Then I give them 2 more markers, so 5 markers total, and I have them make 2 equilateral triangles. And after playing around a little bit, most students are able to come up with something of this figure here. And this is a good activity because at this point of we've kind of forced them to stay on a plane, and not forced them, but they've kind of came up on their own to stay on a plane, and they, since the markers roll, they put them on the table, and so they could kind of hold themselves there. And so the trick to this is, well, what if we give them 6 markers, so 1 more marker, and we have them do 4 equilateral triangles. And a lot of students struggle with this, and you could pause the video if you want to give that a go. But what a student would have to do is we would have to think in 3-dimension here. You would have to put the base on to the table and then hold it upwards. And if you have them working in groups, this really only works if they help each other. So it typically takes the 3 on the table, and you'll have to have one student hold 2 markers and then another hold the other one. So it usually takes teamwork when they start playing around with this. But they start off with a 2-dimensional, stuck on the table, and then they finally realize you have to kind of build upwards. It's a nice little activity where we're using this kind of physical world representation for the edges, these markers here, and they kind of get to play with them a little bit. So, pencils will work as well, for those segments, but nice activity to try out here. And of course, we want to make sure as we're introducing this, we are staying consistent with our verbal representation. So that's going to be a key thing here. And so here we have this diagram where we really want to connect not just our verbal representation, but the physical 3D models, also the 2D models, and then nets. And being able to just kind of go back and forth between all of these. So we want to be consistent and having them able to jump around from these different representations here. Here we go. So here's an activity where we want them to think of a net. So draw a net for a cube. So again, if we were to cut this out and start folding it in 3-dimension, could we make a cube? So a 2-dimensional representation of a cube, right, of a net of this cutout here. And there are many different types. Here's probably a common one. Well, students will kind of start off with a base, and then they'll kind of make some faces that could go up, usually left, right, top, and bottom. And then they'll notice if I fold these up or down, I'm going to need to have another base, right? So the top base as well. And you can actually add this anywhere. I'll just put this off to the right side here. And so we could see if we were to fold this, and it's sometimes helpful to number these as this would be the first. And then as we would go around, you could fold this up, second, third, fourth, and then 5, and with the top base on top there, 6. So putting some numbers on there to guide them so you can see which sides we're folding first, or which faces here. And so here we have an example of another net. Both of these will make a cube, but seeing if they're able to figure out which way these would be folded and just mentally visualizing that. And it's okay to put a starting point so they could kind of see the base first there. But there's a lot of different types of nets. There's no unique one. And just being able, if they could kind of make that visualization from 2D into 3D. Here's an example of some nets that some first and second graders drew here. And so they were supposed to do a net of a cereal box. And we could see activity for them to do on their own. And then, of course, comparing, talking about this as a class. And some of the questions to ask here, are these actual nets of cereal boxes, right? What are they missing? Are they missing some edges, some faces, the bases? What exactly are they missing here? And that's going to coincide with really talking about the vocabulary. So getting familiar to talk about what exactly is, the edge, what's the lateral face. So having that representation is going to be a lot more helpful. So again, saving some of these cereal boxes, some of these shoe boxes, bringing them in, having them play with them. And you could even cut those apart to make nets, right, where they could fold them up and without having to just cut them out of paper, they could see that real physical representation. And vocabulary, right? What is the accurate geometric name for these? Right, so spending a lot of time on that, is it a right rectangular prism? Right? What exactly are they oblique? Are they not? So having that vocabulary there. So here are some representations, some more visualizations of these polyhedrias. And so one key thing here is visualizing these kind of hidden edges that we're representing with dots, right, in the background that you can't actually see them, but we want to denote them. So those become helpful when we start trying to draw these figures. If they're able to visually start seeing them, which of these edges will be hidden, ends up being a bit more helpful transition, but they could figure those out afterwards. So let's draw a right rectangular prism. And so first we start off with a base here, whether it's the top or bottom. So a base, and then we want to make some parallel lateral edges here, right? All of equal length here. So once we have that base, drawing them upwards. And here again, they could start visualizing which ones are going to be hidden. I always just like to make them all solid. And then we'll finish this up with our other base. In this case would be the top base here. And then figuring out which ones are the hidden edges. Pencil is very helpful here because I just go through and I'll start kind of erasing some little marks to make it dotted. But if they could start seeing which ones will be initially hidden, that ends up being very helpful. If they could start denoting that these are going to be hidden edges there. Here's another example of drawing a pyramid, so drawing an oblique rectangular pyramid here. And this time the illustration shows them with thinking ahead of which will be hidden edges. Again, for me, I would typically not anticipate that. I would do my base, kind of draw my whole figure, and then afterwards it makes it a bit easier to figure that out. But anticipation is helpful there. Of course, this is one of those mathematical practices here. So, how would this figure change if it was not oblique, right? If that word was not included. Think of how that would change this illustration here. So again, dealing with vocabulary and as a mathematical practice, right, we want to pay attention to the precision with communicating with others. So that has to do a lot with the vocabulary, so we can be very, very specific. Okay, and then here's kind of our takeaways, doing nets, these 3D models, vocal representation, and bringing them all together here. Okay, so let's look at 17.4 congruent polyhedra. And so here, which of these figures are exactly the same size, right, and shape? So you'll probably be able to see that A, B, D, and E. And if you're able to turn or slide them, or turn, rotations, or slide, what we call a translation, so moving these kind of over, so shifting them around or rotating them. And the colors here are just kind of brought in to indicate that the colors, we're not trying to match them up, so we're not going to pay too much attention to them. We just want to look at turns or slides here. What about these two figures here, G and H? Are those exactly the same size and shape? So we talked about turning and sliding, right? What other movements could probably help us out with that? And actually, a reflection would also be one of these movements. And the word we're looking for is congruence, right? Shapes are congruent if we could do one of those movements there. So reflection will count, a turning rotation, or a sliding translation. So again, to be precise with our communication here, we would say that shape A is congruent to shape B, but is not congruent to shape F. So congruency. So our takeaway, three-dimensional shapes may not be congruent, even if they are not in the same positions, right? May be congruent. So that mental representation in the net starts setting us up to start visualizing, but we want to also be able to start looking at turning objects around mentally, reflecting them, and see if they look similar, right, or are congruent, or are they exactly that same size and shape. And a regular polyhedron here in 17.5, you could play around with this activity at the end of your textbook. There are some figures, some nice cutouts for you to play around with if you're not able to find some actual real life representations.